Hello everyone. In this presentation, I will talk about how to compute planar subgraph isomorphism in parallel. Moreover, I will show how subgraph isomorphism can be used to solve planar minimum vertex cuts. For subgraph isomorphism, we want to answer the question, is there a subgraph of the target graph that is isomorphic to the pattern graph? A subgraph of the target graph that is isomorphic to the pattern is an occurrence of the pattern. In the example, there are two occurrences of the pattern. Subgraph isomorphism is one of the classic NP-complete problems. It generalizes both the Hamiltonian cycle problem and the K-clique problem. Therefore, it is natural to consider restricted classes of target graphs, for example, planar graphs. However, the problem remains NP-hard even in planar graphs. In many applications of subgraph isomorphism, the goal is to find occurrences of small-scale structures inside a larger database graph. This motivates our focus on relatively small pattern graphs. We want that the runtime grows very slowly with the target graph, but the runtime can grow exponentially with the size of the pattern graph. Previous research on the topic includes the randomized color coding algorithm. It achieves small depth, but the work grows quickly and is only polynomial for constant size patterns. Epstein proposed an algorithm whose runtime grows linearly with the size of the target graph. However, its depth does so too. Our randomized algorithm is based on the approach of Epstein, but we reduce the depth significantly. The depth is only linear in the size of the pattern and logarithmic in the size of the target. This comes with a logarithmic work inefficiency. We might also want to count or enumerate the occurrences, but for simplicity, I will focus on the decision version of the problem in this talk. All the ideas can be generalized to the counting or enumeration of occurrences as well. Now, let's think about how we could solve subgraph isomorphism with something like dynamic programming. The spoiler is that it will be too slow in general, but we can use the dynamic program as a subroutine. And with some additional ideas, we can also solve the dynamic program efficiently in parallel. The idea is to separate the graph into two parts by using a set of vertices as separators. So the separating vertices are in both parts, and there is no path from one part to the other that does not also use one of the separating vertices. Then we solve all the resulting subproblems for both parts of the graph. Intuitively, we need to find occurrences for all subgraphs of the pattern in both parts. And then we can combine solutions of the two parts into a solution of the original graph. Two solutions can be combined if they are compatible in the shared part of the graph. In the example, the two partial solutions both map the center vertex of the pattern to the same shared vertex C. Therefore, they are compatible. This demonstrates that we need to keep track of how a partial solution interacts with the shared part. And this means that, in general, the runtime of the approach is exponential in the size of this shared part. And in a general graph, we cannot recursively decompose a graph efficiently in a suitable way. Even for planar graphs, the resulting runtime would still be superpolynomial. Namely, it would be exponential in the square root of n. Fortunately, planar graphs of bounded diameter can be efficiently decomposed. The runtime for the dynamic program is then exponential in big O of the diameter of the graph. Now, observe that every occurrence of the pattern is contained in a diameter k-1 subgraph of the target graph. Recall that k is the number of vertices in the pattern, and the diameter could, of course, also be smaller than k-1. So, to apply the dynamic programming approach, we want to cover the target graph with diameter k-1 subgraphs. We need that every occurrence is contained in at least one of those subgraphs. The simplest way to achieve this is to perform a bounded depth breadth-first search from every node in the graph. In the example, we consider all subgraphs that we get by limiting the search to nodes of distance at most 2. The problem is that in the worst case, A constant fraction of the subgraphs contain a constant fraction of the graph each. For example, this can occur if there is a large star in the graph. The work is therefore quadratic in the number of vertices. To reduce the work, we can construct a breadth-first search tree of the target graph. Then it suffices to consider the subgraphs induced by k consecutive layers in the tree. The work is now only big O of k times n. However, the depth is now linear in the number of vertices. The idea to overcome this sequential bottleneck is to use a randomized clustering of the graph. These clusters are vertex disjoint, and with high probability, each cluster has a small diameter. However, this diameter still depends on the size of the target graph, so we could not directly use the dynamic program on the clusters efficiently. We can ensure that the probability that a particular edge crosses the clusters is at most 1 over 2k. Next, we want to bound the probability that all vertices in a particular occurrence are in the same cluster. For this, consider an arbitrary spanning tree of the occurrence. If no edge of this spanning tree crosses the clusters, then all vertices of the occurrence are in the same cluster. Observe that the spanning tree has at most k-1 edges. And so by a union bound, the probability that one or more of those edges do cross the clusters is at most 1/2. Note that bounding over all the edges in the occurrence would not have been tight enough, and this is why we consider the spanning tree of the occurrence. In summary, an iteration of our subgraph isomorphism algorithm has 3 parts. First, we decompose the graph into clusters. Second, we cover each cluster with diameter k-1 subgraphs using a breadth-first search. And third, we invoke a dynamic programming-like approach. Such an iteration, consisting of these 3 parts, succeeds with constant probability. So a logarithmic number of repetitions give us a high probability of correctness. Subgraph isomorphism is a very powerful tool. If a problem can be solved by finding constant-sized patterns, our result implies a near-linear work and low-depth algorithm for the problem. For planar graphs, minimum vertex cut is such a problem. Intuitively, the minimum vertex cut measures the resistance of a network to vertex failures. More formally, a set of vertices whose removal disconnects the graph is a vertex cut, and the smallest such set is a minimum vertex cut. To reduce minimum vertex cut to a subgraph isomorphism problem, we construct a kind of semi-dual graph. In the semi-dual graph, there is a vertex for each face in the original graph. Such vertices are called face vertices. Moreover, all the vertices of the original graph are also in the semi-dual graph. Now, there is an edge from every face vertex to all the original vertices that surrounded the face in the original graph. In the example, you can see that a face vertex that corresponds to a triangle-shaped face has degree 3, and a face vertex that corresponds to a square-shaped face has degree 4. Note that this semi-dual graph is bipartite. One side is the face vertices, the other side is the original vertices. Now, consider a cycle in the semi-dual graph whose removal leaves the original vertices in at least 2 connected components. It can be shown that this separating cycle corresponds to a vertex cut of half the length of the cycle. Because the graph is bipartite, this is an integer value, so this makes sense. And now we can use this relationship to find a minimum vertex cut using subgraph isomorphism. Because every planar graph has a vertex of degree at most 5, it also has vertex connectivity at most 5. Therefore, it suffices to check for separating cycles of length at most 8, which is a constant as we wanted. Note that for this to work, we also need to extend the subgraph isomorphism algorithm to find separating subgraphs. In conclusion, we showed how to decide planar subgraph isomorphism in near-linear work and logarithmic depth for constant size patterns. We use this result to obtain a more efficient parallel vertex cut algorithm that has near linear work. More generally, our result can be used to obtain parallel solutions to problems that reduce to querying for small patterns. Now, let's look a bit into the future. There are several improvements to the bounds that we think might be possible. Most importantly, reducing the dependence on the size of the pattern graph would be interesting. Moreover, it could be fruitful to investigate implications for other graph problems.